Okay, and please, you can let me know if I'm going over time. Don't hesitate to interrupt. Yeah, so thanks. It's, yeah, okay, it's a pleasure to be here. I decided to focus on a little bit was the work that we did on humanoid robots, because I know that there are many people here who are interested in controlling humanoids. I mean, especially you Ken, and of course up there. So I will first start by talking a little bit about the way that we control robots, combining machine learning and control to make sure that we have very, very fast retrieval, and so we can act in milliseconds. And I'll show how this can be used to control full body motion in humanoids. Okay, so I'll start first with just robot manipulator. This is a work that maybe some of you are familiar with, which was an early work that we did on catching objects flying. And that's the reason why we did that, was to show that we can really go beyond human capabilities in robots and be able to move super fast, even though that robots may not be as fast as a human arm. Actually, the acceleration and torque that it can generate is lower than what we can generate with our human arm. It can catch things that a human will have difficulty catching, and it's typically an object like this one. So I wanted to start with this by just explaining briefly what's the fundamental that we use in order to do this very, very fast prediction of motion under high uncertainty, because there is a huge uncertainty when the object flies. You never really know how it's going to rotate in flight. And also to showcase that it was important to combine both control and machine learning, we took an example like this one, where the bottle is half filled with liquid. And so as it flies, the inertia changes because the liquid is moving inside. So there is no exact model for this. And this is where it's very interesting to identify the dynamics of this flying object. And then use this identification that is done by nonlinear regression technique from machine learning to then control the runtime. So let me explain to you how we are doing that. I'll start with the starting block, and this starting block applies both to just controlling a single arm, as well as controlling bimanual coordination for humanoids, as I will show later, and also full body control. So let's assume that we have a robot that is tasked to just grab this ball. It starts from initial location and has to eventually move and close the finger on that ball. And the ball for now is not moving. Okay, so you have to choose a path. And as you know, in robotics, there are an infinite number of paths that you could choose from. And depending on where you start from, there are going to be another infinite number of paths. So the way that we proceed is to say, well, this infinity of paths, we're going to embed that into a single closed form equation, which I write here as first order. These days, we work in second order controlling for acceleration, but that doesn't matter because you can always write a second order dynamical system as a coupled to first order system. So assume that we're controlling now for such a first order dynamical system, which is similar to what Alessandro earlier presented, and that we have in closed form this functional f of x. And I'm not saying anything about f of x, it could be nonlinear. What I show with such a flow that you see here, which is the vector field, is that this flow has a particularity. It's clearly stable, it has a fixed point, which is on the target. So if you do have that, then you have an infinite number of paths that will eventually lead there. So you have guarantees of stability. And so the good thing is that if your target moves, then you can use an easy trick, is simply to place the frame of reference, the origin of your system, but not just the origin, but also the entire frame on the object, especially when your object is asymmetric, so not a ball. And then if you place now your frame of reference on this, then simply your flow moves with the object. And there exists always at all time a flow that will lead you to the object. So in fact, you don't have to plan anymore. You just have to compute f of x at each time step, and you know that eventually it will lead you to the object. So that's the core behind every single of the technique that I will show here. Now, how do we learn f of x? Well, we can learn it from demonstration. So typically we could have someone showing different examples. That's what we have done for a long time. More recently, we use more optimal control. So we'll solve this with typically an MPC and get lots of different feasible trajectory and then use these as demonstration. The reason why we do this two-step process is that we really want to have a closed form solution. We don't want to do optimization at runtime if we can avoid it. Once we have this example of feasible trajectory, then we can learn a function. And you'll say, okay, I'm going to use machine learning so to learn a function of this type. If x dot is 3 or 7 dimensional or whatever is the dimension, I'm going to now use a nonlinear regression technique to predict x dot as a function of x. And I could do that with what is called SVR, which is support vector regression on neural networks. And you can do that, and you're going to have very accurate estimates. The problem is, as you can see here, is that the estimate will be accurate up to a certain point. So typically what will happen is when you reach the ball, which is your fixed point, your velocity will be very close to zero, but numerically it will not be exactly zero. And so often what will happen is that you still have a little positive drift, and then you may eventually not, hit first of all with a non-zero velocity, and then move further away, and so move the object away, but in an uncontrollable manner. And it's the same. You could use any of those techniques. So this was our starting point. We wanted to have such a functional. We wanted to be able to learn F, but we needed to make sure that we had the stability. So what we request is to have convergence to a fixed point. So we would limit that all the flow will vanish. And we can guarantee that by using typically Lyapunov stability. But now our problem is that we have neither F nor V. So we can estimate now F and V, or one of the two, from the demonstration. And so the way that we proceed, that was the very first work we did, and then we used different also algorithm. I'm not going to go through all of them, but we started from this demonstration. We said, okay, what if we use one of these standard machine learning technique, which is called mixture of ghost function? So we can combine a mixture of ghost function, which are illustrated here. So each of these ellipses represents a slice in a ghost function. And I have now a joint distribution over the velocity that I want to predict and the position. But what I want is to predict the velocity. So from the joint distribution, I can compute the conditional. So I can condition the velocity on the state, as I write here, and take simply the expectation over this conditional. And the interesting part is that for every single machine learning technique, it's the same for our network. You end up, when you do this, to have a closed form solution. It's an analytical equation, and usually it's continuous. It's C1 at least. It's sometimes even C infinite, depending on the kernel that you use. So with this closed form solution that we chose here for the mixture of model, what we also showed was that the elements that you have in the closed form solution, the unknown, which are a set of matrices that I write here as AK, as well as vectors, BK, these unknown that you estimate normally, you can actually constrain them to satisfy the constraints of having a vanishing. So in this very first work, what we did was to choose a Lyapunov function. We just said, okay, we just want a quadratic loss and make sure that our function vanishes at the origin of our system. If you do that, then you can derive explicit condition for these unknown parameters. You can have an explicit condition on the stability at the target, which is made of these BK and AK. So BK the vector, and AK the matrix that is associated to each of the ghost functions. And you can also enforce that the energy decreases everywhere, so that you can enforce this as condition on this value. We actually did similar things for other machine learning techniques. So you can impose these constraints for stability on different of the optimization. In this one, we end up with a constraint optimization problem that we can solve. Typically, we use maximum likelihood. You can use mean square. You can also do the same thing for neural networks, and you can do the same thing for support vector regression. Actually, for support vector regression, it's quite nice because you end up with a convex problem, whereas for the other two, you end up with a non-convex problem. So sometimes it's less ideal. But what you have then in the end is the following. So you start from this demonstration, you can write this explicitly, and then you get your flow and it's stable. And just so that you know, we also did it the other way around, as opposed to fix the Lyapunov function, which is highly constraining, especially if it's just a quadratic loss. We also went and learned actually an estimate of the Lyapunov function. And then we get the f of x by taking the gradient of v. Okay. And the advantage also of this is that then you can train even an unstable dynamical system. So you could use neural networks, you could use SVR, you can train it, you don't care whether it's stable or not, and then you can restabilize it with this method. Now, again, going back to what I said before, why do we need machine learning? Typically, when you want to catch an object, whether it's a bottle half filled with water or an object like this one, the difficulty is to predict the trajectory of the object. So predicting the subject dynamics can easily be done by just having a few examples. So you'll just throw the rackets and show different examples, like here, or the different objects. Usually 20 of those throws, if they're really spanning, the complexity. So you make sure you throw it with different initial translational and rotational velocity to respan the type of non-linearity that you can observe. Like we did here. So you have someone throwing this, you have camera tracking the position of the handle, and then you use this as data. And then you can train. And you can train a system, which we did. We then contrasted all different machine learning technique. While the neural networks were the most accurate, our problem was that it was drifting. Again, similar reason as before. A little bit of also problem of overfitting. And the drift for us was a little catastrophic because you want to predict ahead of time. So you prefer to have a less accurate system, but at least not unstable. So for this particular application, simple vector regression was the fastest and drifted the less, even though it was a little less accurate. So given this closed form solution, similar to what I presented before, then we can use an extended Kalman filter and fit this learn model to predict the trajectory. Now, once you have the trajectory of the object, you're not completely done. You have to decide where you're going to catch it. So for that, we need to have a representation of the workspace of a robot. And I'll spend some time explaining to you how we can learn this representation of the workspace of a robot and use it for collision in humanoids next. But here, so what we could do was to learn that. So let's assume we have this. And then if you have this representation, then you still have to decide, where do I catch it? I see the trajectory. I can predict ahead of time where the object is going to fly. I know the volume of my workspace, but I still have quite a number of places where I could catch the object. So which one will be the best? And so you can decide on this by having a representation, a probabilistic representation of your workspace. So if you have a probabilistic representation of your workspace, what you want to embed in this probabilistic representation of your workspace is the most likely posture. I mean, the posture that is most likely to yield success. And the posture that is most likely to yield success is the one that is the furthest away, obviously, of things that you want to avoid, like singularities. It's also the one that is the densest, which means that that's the one where you have most different posture that are feasible. And by posture, I mean here not just position, but orientation. So we may be in 7 or 9 degrees of freedom when we want to represent all of this in terms of also the posture of the finger. And so you can represent that, you can sample your space, I'll come back to that, and you can have a representation of different points in this high dimensional space that are reachable from different orientation, and the densest are the best. So we'll choose the densest one. Why? Because at one time, as our prediction moves, and as I said, we are not super accurate, so we keep repredicting each time that we see the object, which is slower. Of course, we sample at a slower frequency than we predict. Each time that we re-estimate the object, we're going to re-estimate how we're catching it, how we're orienting. So it's very important to go to a place where, if need be, I can still reorient myself very rapidly at one time. So here is how it works. We have the predicted trajectory of the object. We have a rough estimate of where we want to catch it, and off we go and we start moving. And we start moving with the dynamical system. Okay, so we need to move there. And at one time, when we get a new estimate, then we have a new location that we may predict, which may be far away from the first one, or not too far, and we need to relearn that. So we used, by the way, human demonstration in this case to learn different trajectory to catch, as you can see here, from the robot viewpoint, so that we had feasible kinematically posture. And then from there, we learned a dynamical system, the same way as I explained it before, and we use this in combination to be able to same trick. We used also the trick of putting the origin of the system on the point where we wanted to catch, such that we will have our dynamical system moving with this point. Now we tried to do the same with a full humanoid robot, and I will explain to you how we did that. So similar problem, we need to be able to predict the object trajectory. So for that, we use the same system as before. And then we need to predict the best catching pose prediction, which we can do by a generalized inverse kinematics model. And then we need to control for the arm and the hand, which I will not discuss here, but we have another ways of doing. Now, this inverse kinematics that we need to compute at runtime, we wanted to have a model which will be the best possible. So, yeah, and the last thing, of course, we need to stabilize. So for that, we used standard stabilization. So in order to give a little bit of knowledge to our system, we went back to human demonstration. We asked people to catch object in flight, as you see here, and we tracked the whole body motion, actually mostly the upper torso. So that's what you see also on the right-hand side. I'll just play that. So we have a fairly accurate representation of the motion of the arm, the torso, and the wrist. And we use this as a nominal system to learn the dynamical system that control for the torso, the arm, and the grip. Now, in order to decide on what will be the posture of the joint of the human robot, we contrasted two things. One is to use the standard pseudo-inverse method that you have on top. And the second one was to have a human-like inverse kinematics. So by human-like is simply to do the more pseudo-inverse, but use the human dynamical system, the human learned dynamical system that represent the posture that you like to have, and to take this as the reference for your pseudo-inverse. And so you want to be as close as possible to those joint trajectory. And in fact, it gives you better results. It gives you much better results, especially results that are closer to things that are stable. So you still have to stabilize after that, but at least you're less far away from stability. For the stability, we really are not, this is not our strength, so we use things that exist. We simply compute the center of mass, and then we use EMP planning that you see here. The only tiny difference that we did was to look at the displacement of the center of mass. And we learned that displacement of the center of mass also from the human demonstration. This is what is represented here. I hope you can see my mouse. So you see this ellipsoid here represents, similar to what I showed when we were learning the dynamical system, this ellipsoid represents the region that is feasible for the center of mass to move, and these are the 2 feet. So this is a region that was feasible for certain posture. And if you can model that, then you can force the center of mass to never exceed that. So in other words, we have a stable point that will be in between, and this region is the feasible one, and it generates a little bit like an impedance type of control system. You will allow your center of mass to fluctuate in between this region, but not outside of that, because it's a possibility. So just building that from demonstration allows you to make sure that you have more stable. I mean, you don't exceed this usually. You still have to rely, again, as I said, on ZMP planning, but you have less chances to get into unfeasible solution. So this is the simple ZMP planner that we had. And then we ran that. So in simulation, we could get it to run really nicely. Here, actually, the simulation is slowed down by a quarter. But on the real robot of Coman, we never managed to really get this to work, because the robot was not quick enough to be able to catch. And at the time also, we did not have a hand to be able to catch the object. So yeah, I will look forward to be able one day to implement that really on full body control with a real robot. Here are also a couple of other videos where you can appreciate the type of posture that you can have, which are a little human-like, and there are different ways in which you can catch with different orientation of the arm. So this was very, I thought it was nice and early work, but very modest. It's a simple approach for now. Now, you really tell me if I'm out of time. I don't know how long I have. I still have a bit of time, right?
Yes.
Okay. So now I'd like to turn to a crucial problem, of course, of robotics, which is how do you handle obstacles? And you have obstacles, both external obstacles, of course, when you navigate, as well as internal obstacles, which is your own body. And this is particularly true for humanoids. So how can we then still keep our framework, which is this dynamical system, but still guarantee that you will reach a target, for instance, but still also guarantee that you will never penetrate obstacles, whether it's your own body or external obstacles, and most importantly, what happens when these obstacles change and move. So So we wanted to start again from this nominal system that I've said is x dot equal f of x, which has all this nice property. But then we like to be able to modulate it in such a way that if a human comes comes around the robots, then we're still avoiding it. And we're still doing the task that we want. So see, pick up objects, put them wherever you want, but still at runtime avoid an obstacle when it's coming. So it turns out that we can do that while preserving the nice property by simply generating a modulation, which I write this as m of x. And so for now, I'm just saying you have a functional f of x, which has some guarantee, like asymptotic stability and a factor. And then you want to change it and you're going to modulate it. And for this, you just do a multiplication, m of x times f of x. And I haven't said anything about m of x. So we've used this extensively. I'm going to present now this modulation m of x only for obstacle avoidance. By the way, this can also be used for generating impacts, so generating more forces at impact as opposed to stop at the targets and to throw things away in the same spirit as what Alessandro presented before. So how can we use now this m of x to modulate the flow around an obstacle? Imagine that you have an obstacle, and imagine that your obstacle has an envelope, and you know this envelope. And this envelope is given by a functional, which I'm going to call gamma of x. And this may live in Rn. So if it's in joint space, as we will see next, it can be very high dimensional. If it's Cartesian space, it's going to be 3D. Assume that you have this envelope and that you have something even more than this envelope, that actually this envelope gives you a notion also of distance to the obstacle. And now we set that on the obstacle itself, the envelope is an isoline, which has a value, and we set this value to be 1. And so by default, if this envelope represents a distance, then that means that away from the obstacle, this envelope is positive and keeps growing. And inside the obstacle, it's inferior to 1. So the envelope is exactly 1 around the obstacle, inferior to 1 inside, superior to 1 outside. If I have an envelope and this is a continuous function, and it's at least C1, then I can compute in every single point in space a normal to the envelope. And then I can compute here also a plane, which is 10 meters. So if I have this, I can then deflect my flow. Now, how do I get this envelope? I can learn that with nonlinear regression technique. I will show to you how we can learn this typically to avoid obstacles which are made of the body of the robot in the next presentation. But I'll start first by explaining how we can use this envelope to deflect the flow. So our modulation m of x needs to be constructed. So usually you do an eigen decomposition when you have a matrix and you want to observe what this matrix gives you. What we're doing is an eigen composition. So we're going to build m of x by composing m of x as a set of eigenvectors and eigenvalues. The eigenvectors will be taken from this representation that we have of the obstacle. So the first entry of my eigenvector is going to be the normal to my surface. And then all the others are simply, orthogonal direction from the hyperplane. So I can do that, and that gives me these 3 variables that feed into my eigenvectors. And then I can also choose the eigenvalue to deflect the flow. I'm going to explain this, but you can check the paper if you're interested. I'm happy to discuss this later. Now let me represent this with a very simple system. Assume that you have a ball and you have a nominal linear dynamical system. Simple linear dynamical system. Okay, you're stable at this attractor. You're moving linearly towards this. I place a ball here. Recall, gamma equal 1 is the envelope, the isoline around the obstacle. If I modulate this nominal dynamical system with this, okay, then I will get the following. I get a deflection, as you can see. The flow is actually moving along the obstacle and then eventually reaching my obstacle. So it's quite nice, and you preserve the properties. And we can do that for complex obstacle, and we'll not go all the different derivation. But what you have here is an example of a complex obstacle. You see it's non-convex. I started with a ball, but of course you can do it also with non-ball. Every single of these points represents the flow of your dynamical system, and you see how it's deflected around this very complex obstacle. So we can do it also with concave obstacle. The only little constraint is that we need to have what is called star-shaped obstacle. That means that all the obstacles need to meet in one point. That's one constraint. But on that, we can handle quite complex shape. And we can also, interestingly, handle obstacles that are moving. So here is an example. You have all these flow, which are computed at runtime, and these are the infinite number of paths that you have to the attractor, which is located here. And here is an obstacle that moves. And observe how the obstacle will deflect at runtime all of this flow, okay, having them move away. You could also have it rotate. You have again all these nominal dynamical systems, which are all going to the attractor, which this time is placed here. And you have this obstacle that moves around. And observe how it's pushing at runtime all these different flows and moving them. So we have started implementing that for control of navigation. We have here, it's a Segway-like platform. Actually, it's a wheelchair that's been developed by Tsukuba University, with whom we collaborate on that. And what we're controlling is the navigation of the wheelchair. And we are detecting the pedestrian at runtime. The pedestrian represents these moving obstacles, as you can see, it's a flow of them. And we have to avoid them at runtime while avoiding also static obstacles, while still keeping to move such that the robot will go from A to B, but we still intersect. And even though we are all in a crisis, we managed to start getting some of some crowd in the city of Lausanne, where we live. And we started doing the same with now real-time tracker, as you can see that, and avoiding pedestrians live in this, which is a supermarket in the city of Lausanne. For now, luckily, there was no collision, and it worked really well, and so we have submitted that work. Now, I said we can deflect the flow if we have the boundary around the obstacle. How do we get this boundary around the obstacle? And when it becomes quite interesting to get these boundaries, when we have boundaries that are really non-convex, very complex and in high dimension. And this is the case, particularly when you want to avoid self-collision. So you have collision of this type, typically when you have two robotic arms and they have to move together, then you may want to avoid self-collision like this, and you may want to learn to avoid each other. Okay? And so you have the same, I'm just jumping directly to the humanoid control. You have the same when you want to control for humanoid motion to pick up a box like this. We're fortunate enough in the lab to have the iCub, which I really like because it's a platform which has really a lot of degrees of freedom, and in that sense, to me, it's really magic to have been able to put so many different motors in such a tiny space. But for a long time, I felt a bit frustrated because we were barely using all these degrees of freedom. That means we were always moving the robots, standing and picking up objects from above. But what fascinates me is to be able to pick up objects when they're lying on the floor, and you really have to crouch down and pick them up and use all this notion of the torso, bend the knee, bend the ankle, and then pick up the object. And I'm particularly interested to do so sideways or within the legs. Now, what we quickly found out when we tried to do that is when we use the inverse kinematics is that you will often end up in self-collision. And it's very difficult to find a path which doesn't self-collide. And as you know, we want to do that at runtime. And so we want to be able to compute that very fast. So how can we embed then this notion of what is the feasible space of the robot, or in which it can move, feasible joint space? So what we did was to sample, because we have the kinematic of the robot, so to sample all possible posture from the legs, the torso, etc., and then to learn a region. So you have to think of it in high dimension. We're in 29 degrees of freedom here. So and the total number of dimension is 31, but you can reduce it because there is subsymmetry. So and here we also froze the neck, and we did not care about it. So we ended up with 29 degrees of freedom, and we need to learn a model. So we do sample all of this posture, and then we sample all the collided motion and the non-collided motion. And this is where machine learning comes in. You can learn then, this is a representation. Imagine that the green represents the non-collided joint configuration and the red represents the collided joint configuration. Of course, this is a slice, you're in 29 dimension, you cannot visualize that. What you can do is to learn this gamma function, which is represented here. You can have a closed form representation. The first approach we did was to use supervector regression. Then for this particular human robot, we had to go to neural networks to really have a very accurate estimate because it's so complex. So you can get this, and once you have this function, then it's continuous and it's also derivable. So again, you can use the same trick as before. You can represent the region away and the region inside, the exact boundary, sorry, the region outside the collided boundary and inside the non-collided boundary. So you have this representation of your feasible workspace, and you have an explicit expression for this boundary, even, I mean, irrespective of how complex it is. Now what you want is at runtime to always move away from that. So you want to use a gradient away from this boundary, which you can compute because you have this closed form solution and it's derivable. Now for this, we had to formulate this as a QP problem, which was solvable at runtime because we could no longer, at this stage, we still don't have a solution where we can guarantee the impenetrability as I had before, because often this non-convex boundary is so concave that we no longer have this star shape criterion that I mentioned before. So you have here a representation of this boundary live. So observe that on the right-hand side, you have the robot bringing this right arm close to its left arm. And you have on the left-hand side a representation of how this boundary is moving as you come closer. And so it's like this red region is starting to eat up all the space. And if you slightly move above, you see how this boundary is moving. It's really important to understand that this boundary is not static. In fact, the boundary across the joints keep changing depending on how you move. When you crouch, then the feasible space that you have for your arms is going to shrink. As you stand up, then again, the workspace, the feasible workspace for your two arms is expanding. So this notion of shrinking and expanding, we have it at runtime because we are currying for this boundary at runtime, which depends on the joints. So we don't have to we don't have to re-estimate it with optimization. We have it in closed form. We have it as a function of the posture of all the different joints. So we can compute this in real time. And this is the QP problem. I will not spend too much time on this, but it's really nothing much fancy. We start with our functional F, which is now a linear dynamical system in joint space. So we set it as being a linear system, dynamical system in joint space. We can compute the joint limits that we have, and then we can move with the gradient. So we want to always satisfy that we are never gonna hit the boundary, and that we're gonna also move in the direction of the gradient. So this is a constraint, an inequality constraint in the QP, and the rest is a standard optimization for optimization of flow. So when we do that, then we can compute similar. You may recognize the previous plot. This is the boundary. And then as we're computing with the QP, you see that we move away from the boundary, and the boundary basically vanishes and gives you a lot of free space. And then if we come close again, then the boundary, the region of the invisible workspace grows again. This is the case because here the left arm is coming close to the right. So we can then at runtime use this to get the robot to crouch down and pick up this object. On the left-hand side, you have the inverse kinematic solver, that's traditional that we use first. And then when we use the self-collision model with the QP, then we get a feasible posture at runtime to get the object. Here are two videos that shows to you that it's possible to really implement it on a real robot. So going down, picking up the object eventually. Here, when the object is lying on the front, and then when the object is lying on the side. There are more examples, more video in the paper that was published by Michael Koptev, who is the PhD student who developed all this work jointly with Nadia Gregoria. And you have a QR code if you presented that earlier on, I think. So yeah, see, this is an example of successful picking up. Small, very, very rapidly, small mention also that this dynamical system can be used also this dynamical representation for manipulation navigation. We can combine the two. So I'll go a little more quickly here. We can get now dynamical system to also control for the two robotic arms. So this is a crouching, okay, picking up the object, and then now we can use the flexibility that we have by perturbating the system. So I'll show you here example on the actual real robot, picking up the object, moving it upwards, and then we can generate perturbation, okay, and it will still adapt to this different perturbation. We can push on the different direction, and it will adapt to that. And this is the same principle of the dynamical system. You have your target that moves, and same principle, the target is the origin of your system, and as it keeps moving, then the two arms will adapt. Now observe that the robot doesn't try to reach it everywhere, and it will stop before it actually falls, with the same criterion as I mentioned before. As soon as we exceed the region that is stable for the center of mass, then we'll stop. We can combine this notion with also a dynamical system for navigation. So for that, we had two different dynamical systems, one for bringing the two arms to pick up the object, and another one to bring the center of mass of the robot to the actual attractor. This is really, think of it as the planning trajectory, and we're not doing locomotion. We're using a very standard locomotion pattern here. No smartness there, but what we control for is the direction in which the center of mass should move. So as soon as the objects disappear from the workspace of the robots, then it will walk up to the place where it can pick it up, and then go down and then crouch and pick it up. And yes, these are different examples. This is the last video. So with the robots, of course, it's sped up 1.5 times. Observe the adaptation. So if you rotate the robots, then it will recompute a feasible trajectory, and then eventually come and crouch down and pick up the object. And the line here represents the nominal trajectory that you want to follow. The robot will always come back to this nominal trajectory. That's also a secondary system that I haven't explained, which Nadia's figure area that you see in this video developed to allow the system also to come back to a reference trajectory. So here is the adaptation of the robot to get eventually there. Okay, I will stop here. Luckily, we have been offered the opportunity to present all of this work in a book that will appear in the spring 2022. And there will be also all the source code and the different publication available there. And so with this, I want to thank warmly, of course, all the people who worked on this. Mohamed Kanzari was the first person to develop the idea of this stable dynamical system. Sina and Nadia worked a lot on the catching in flight, and especially Sungsu. Luca is behind all the obstacle avoidance, as well as Michael Koptev. Michael Bombile worked a lot on with Salman Farji on the navigation and stability of the locomotion, and Diego is behind the wheelchair robot. With this, I will stop, and if there are questions, then I hope we have time for this.
Thank you very much for the great presentation. Actually, there are still 5 minutes or 4. So are there any questions?
Well, I have more of a comment than a question. This is Roy Featherstone. Aude, your work on collision avoidance reminds me of very old work done by Dan Kodicek in the 1980s and 1990s. Are you aware of this early work?
Of course, yes. Actually, it's even older than that. We started from Jean-Jacques Slotin's very nice work that is not cited as much, appeared at the same time as Usama Khatib's potential field. So quick response. We really prove impenetrability for also concave obstacle, which has not been done by Dan Kodicek, and I really like his work, and we're very much influenced by that. Jean-Jacques Slotin's work introduced in 1997 the notion of harmonic potential, which is underlying the solution that we're providing. So this harmonic potential is really the core of this notion that you have an explicit shape for an obstacle, and then you can use this to deflect and guarantee that you have non-penetration. So this is really much more aligned with what Jean-Jacques had proposed first. He had already a solution for flat slope, so for planes. I think there is someone typing heavily, so I don't know who this is.
Oh,
yeah, I think it's you. And so we extended it. This is why also he's a co-author on that. We extended it to be able to handle more complex shape, so the star shape that I presented before. So this is definitely aligned with this spirit, and it's one step it's an extension in this sense. And we also extended it to include the dynamics, so a model of the dynamics of the obstacle, which wasn't there, so that we can avoid multiple obstacles, and also the multiplicity of the obstacles in a closed form manner.
So Aude is up there speaking. I have a very, very difficult question for you. I'm sorry, but I have to ask you, is it okay? So first of all, I would like to thank you because I know that you are completely constrained and you make it for today. Thank you very much for taking from your time to speak to the issue you are facing. How did you get the clearance to do the experiment in the center of Lausanne?
Difficult question. It wasn't difficult. I thought it would be difficult. It wasn't at all.
Okay.
But that's because regulation already allows in Switzerland, and I think in many countries in the world, that you can have autonomous platform navigating as long as there is someone on the platform. So that's why it works, because it's a wheelchair. So we have someone standing on a wheelchair who can stop it at all time. And we also have a secondary experimenter who can stop it at all time. That's how we got the clearance.
Oh, that was a wheelchair. Sorry, I didn't get this. I thought
yes,
it was a okay.
Yeah, it doesn't look like a wheelchair. It's because it looks like a Segway, but actually it's a wheelchair that allows people to stand, which is really beautiful. So this allows people to be at the same height as other people, as opposed to be below. So yes, that's how we got the clearance. And we also, I must say, the fact that that we're in this pandemic makes it easier for us, because everybody's wearing a mask. So we don't have problems when we're recording faces because they're already hidden. So there are, yeah, that's ironic. But yeah, any other difficult question up there on the humanoid control fire?
I have a couple of them, but I will ask you later.
Hello, Aude. Thank you for this impressive presentation. Thanks. I have very detailed questions regarding the stability of the dynamical system that you presented in the beginning. So first, you said like you're employing this quadratic Lyapunov function, and then later you said you also learned the Lyapunov function. I think you're referring to this weighted sum of asymmetric functions. So, but when you enforce the stability, to what I understand, you are just using the first component of the weighted sum of asymmetric functions in the stability proof. So why
for the second one or for the first one? Because for the first one, no, it's a complete, it's fairly, in that sense, it's a quadratic loss. Huh? So you have a quadratic Lyapunov function. So you enforce that the entire energy of the system vanishes.
But when proving the stability, are you making sure of all the components of this entire weighted sum of asymmetric functions?
Now you're talking about the other part, the second work, when we are learning the Lyapunov function itself. I believe so. I will have to check. If you found a mistake, please let me know. But as far as I remember, it's been in 2014, so I'll like to look at it. But as far as I remember, we do, definitely. This work, by the way, we have stopped using it nowadays. Because we're also collaborating with Selfcollision, we're doing. We are no longer really not always using Lyapunov. We're using contraction theory to prove the stability of the flow, which actually I did not even mention. But for the stability also of the obstacle avoidance, we prove it with contraction, because otherwise you couldn't. With Lyapunov, it's too conservative. And most recently, we have a paper also, but it's submitted, that contrasts using Lyapunov versus contraction theory. Now, for the quadratic sum, I believe we do. I will double check, but I think there was no hole in the proof. If you do find one, please tell me, but then we'll check it. Top of my memory, I don't think it's the case. But in general, learning this Lyapunov function and then stabilizing the flow is not something we do in practice. We much prefer directly learning the flow at stable flow. It's just, I thought it was a nice idea to offer that to other people who would prefer to use, their own nonlinear regression technique, or start with a nominal dynamical system that they know, so that they could restabilize if they wanted to. So I thought that's a nice approach. But for us, frankly, like you've seen, we usually learn directly our own dynamics, whether we do it these days with optimal control separately or directly from human demonstration. So yeah, But let me know, just in case you find something, then definitely we need to correct that. I don't think it's wrong.
Okay, thanks for this further information.